Another interesting application of linear algebra is the function fitting. Every time we develop in some sort of mathematical or physical model, we need to fit some sort of function to that model or to design such a function which will describe that model. Let's start with the simple problem of fitting straight line to given points. The points are given by coordinates xi and yi. And we have totally, for example, n points. So points are going from 1, 2, and so on until you get to n points. You can start selecting those points from left to right or in any other order, but for simplicity we'll go from left to right. So this first point will be x1, y1. Second point, x2, y2. Third point, x3, y3. And so on until you get to the last point, which is xn, yn. The line model is given by y equals ax plus b with two parameters. So y equals ax plus b. This is the equation of that line. And we will have two parameters a and b. We would like to find such a parameters a and b that will fit as close as possible to those green points. Since the data is noisy, clearly we cannot pass this line through all of the points. But we want the line to be somehow closest possible to those points. The goal is to find a and b such that make the line close. So we technically need to define what it means closest possible. One of the possible definitions is that we want to minimize a sum of absolute vertical distances of all points from the line. We need to define some sort of cost function which will measure all of those errors. So you'll have line of error here and error to that line here and all of the other lines, how far away they are vertically from that red line. Now, you want to define equation which will define the cost function, which means total error for all of the points around. This is how we will define it. We want to find argument minimum on all of the possible a and b of some given cost function. And we will define it the following way. Sigma from 1 to n, which means on all of the points, of absolute distances that we have. And absolute distance is yi for each point I, minus our model, which is axi minus b. The problem here is that absolute value function is not differentiable, and we will not be able to use Fermat theorem about zero of derivative at extrema point. So you will not be able to find easily the point which is extrema or minimum point for that kind of expression. And this is why we need to modify it a little bit. We want still to keep the same idea, but to make it differentiable. And this is where square error comes handy. Instead of absolute values, we could use squares of the errors. So our cost function will be basically squares of the errors instead of absolute values of the errors. So you'll modify it like that. Pay attention that those numbers that are coming here in that thing are our errors. This is error I. So this is error n minus 1, and this is error number 1, error number 2, error number 3, and so on. Those are the distances that we are measuring, and we are doing that error I squared and adding all of the errors. We want to find such a and b which will minimize sum of square errors. So it will be argmin, minimum of argument on a and b, for e1 squared plus e2 squared plus, and so on, plus en squared. We want to minimize that expression. For that kind of expression, we can find minimum, but still it's too complicated because we need to write each e as a function of x's and y's, and then to find derivative with respect to x, and then to find system of equations, and then to solve the system of equations. It's pretty complicated, long process. So we want linear algebra to help us somehow to solve that problem. And this is how we will do it. Let's write explicitly what those errors are. So from the equation on the line, we will see something like that. So our y1 will be x1 multiplied by a plus b, which is equation of line, plus error number 1. And it could be positive or negative, depends on the side the green point takes compared to the red line. Now, y2 similarly will be x2 a plus b plus e2, and so on until you get to yn equals xn a plus b plus en. So this is technically a system of equations that we can write in matrix form, which is very convenient here. The matrix form will look like that. You have y1 vector to yn. This vector we will call it vector y equals matrix. This matrix will be n by 2, and we will call that matrix A, and it will include all of the x coefficients and 1s. It will be x1 1, x2 1, and so on. So here we will have only 1s, and here we will have x1 to xn multiplied by coefficients a and b, and plus error vector. Now pay attention that both things are completely equivalent. So the matrix system is exactly the same. We will call z vector x, because this is what we want to find, because we are looking for a and b, such that that thing squared will be minimized. We will call that thing e for simplicity. Now, what we actually want to minimize is dot product between e and e. So we want minimum of e dot e, and this is what we are looking for. And we are looking for a and b, which will minimize the dot product, which is basically e squared. Now, from the properties of dot product or inner product, we know that we can write the same thing as e transpose e. Now let's write that explicitly. So from here you get y equals ax plus e, which means that e equals y minus ax. So let's put it here. And this is the expression that we will want to minimize, and to find such a and b that will minimize that expression. So it will be y minus ax transpose multiplied by y minus ax. And that's it. Let's simplify it a little bit. So what we know about transpose, that we can do transpose of each part here. But when you're doing transpose of multiplication, we need to switch sides of the matrices and to do transpose of each one of them, which will make it the following way. So it will be y transpose minus x transpose a transpose multiplied by y minus ax. Now we can use distributive law and to find what it equals. So it will be the following. phi transpose y minus x transpose A transpose y from this one together with this one, and then this one with this one will be minus y transpose AX, and then this one with this one will be plus x transpose A transpose A and X. Okay? Now we need to pay attention to something very important. First of all of those terms are just scalars. Because, for example, this is vector y transpose is z kind of vector, and vector y is z kind of vector. Their multiplication will just be a single number, which is scalar number. The same thing for all of them. It will be scalar, and this one will be scalar. You can see that by very simple example. So if x transpose will be vector like z, A will be matrix like z, y will be vector like z, so multiplication of z thing by z thing will be vector like z of the same size, and multiplication of z vector by z vector will be a number. So this is how it works. Now, pay attention that if you have some scalar, alpha, and we're making transpose of that scalar, it's still the same scalar alpha. Because this is just constant number transpose, it will give the same thing. Which means that if you will take that thing and we will make transpose of it, we get exactly the same number. But what is transpose of that thing? So y, t, a, x transpose is technically the same thing as y, t, a, x, but it equals, first of all, we're starting with x transpose, which is that one, then a transpose from this one, and then y transpose transpose, which is y. Pay attention that this thing is exactly the same thing like you have here. So technically you can simplify that expression and to write the following thing. You're writing y transpose y minus twice x transpose ay plus x transpose A transpose A X. Now we want to use Fermat theorem, which states that the derivative as derivative of something that we want to minimize or to find minima with respect to x should be 0. This is Fermat theorem, which is true for calculus, and this is the same thing for matrix calculus. Also, I need to mention a few things from vector calculus and matrix calculus. A few expressions that I will not prove, but I will just show you. First is the derivative of function xt multiplied by some matrix M with respect to dx is A transpose. So this is first formula that you need to remember here. And second formula is d of x transpose A transpose A x with respect to x equals twice A transpose A x. Now we can continue our computation here. So we know that we want to do derivative of e dot e with respect to dx, and this is derivative with respect to dx of y transpose y minus twice x transpose ay plus x transpose A transpose A x. And this equals, based on the formula that I just gave you, first of all, derivative of y transpose y is 0 because this is not a function of x at all. So this thing disappears. The second thing will give you minus twice A transpose y, And the third thing will give you plus twice A transpose A X. This should be some matrix A. Pay attention that here I assumed that all of that matrix is that thing A here. And then I use that rule to get here. Now, all of that should be equal to 0. What it means that you can cancel the number 2 here and number 2 here. And what you get is basically A transpose A X equals A transpose Y. Now, to solve that equation, we basically need to multiply both sides from the left by A transpose A inverse. So this is what we do. We take A transpose A inverse, if it exists, multiplied by A transpose A, and then multiplying that by X equals, and the same thing from that side, A transpose A inverse multiplied by A transpose Y. But pay attention what happens here. This cancels with this one. And then what you get is the final formula for least squares, which is X equals A transpose A inverse A transpose Y. This is called least square solution to the system that we have here. This solution minimizes the square error of vertical distances to the model of the line. But this is not only that. You can expand it to many other things. We will see that in a second. For example, you want to fit some other polynomial, not straight line, maybe quadratic polynomial. So you have a bunch of points, and those points are distributed like that. And it looks like a parabola that you want to fit your model to. So your model probably will look something like that. And you want to find that line which will be closest to those points in the same sense of minimal squares of distances or errors that you have from those points to your model. And let's say your model will be like that. So y will be ax1 squared plus bx1 plus c. And you want to fit to that model. You write the same thing in matrix form. You'll get something like that. y1, y2, yn will be equal. Now we're changing the matrix a little bit. x1 squared, x1, 1, x2 squared, x2, 1, and so on, until you get to xn squared, xn, 1, and then you multiply. Now you have 3 parameters in your family, a, b, and c. Those are the numbers that you want to find for the best fit. And so you have them a, b, and c. Pay attention that when you multiply in the first row by all of those parameters, you get that equation for the first point. When you multiply in that row by that column, you get that equation for the second point, and so on. So as many points as you want, you can put in that matrix. Now, you need to add some error, right? So this is, again, E1 until you get to En. And you want to minimize square of that error, which is sum of E1 square plus E2 square plus E3 square, and so on. Now, again, you have in matrix form, you have y equals ax plus e. The solution of least squares to that equation we know already from the previous slide. And the solution is x, which is ABC in that case, equals A transpose A inverse A transpose and Y. This is exactly what we had in the previous slide. So the solution is exactly the same as it was before with linear function. More than that, you can use polynomial with any number of coefficients, and then just the matrix A will change, but the solution will stay the same like that. More than that, you don't have to use even polynomials. Inside of that matrix, in matrix A, you can have any functions of x1. It could be f1, f2 of x1, and so on. So it could be basically anything until you get to f1 of xn, f2 of xn, and so on. So those functions could be anything. Just your general model will be y equals f1 of x1 multiplied by a plus, it's not x1, it's just general x, and then some other function of x multiplied by b, and then some general function of x multiplied by c, and so on. Depends on number of parameters that you want, which are a, b, c, and so on. The size of that matrix will change. But other than that, you still will have exactly the same solution like that. Which means you're not only capable of fitting polynomials, you can fit many, many other functions where in those functions all of the coefficients are linear in terms of addition. They multiply just some given functions. This makes that kind of algorithm one of the most popular algorithms. So least squares is very popular in functional fitting for all kinds of applications.